Rachel will be talking there, amongst others. Lots of speakers that I recognize. Should be pretty cool. I think the YouTube stream is meant to be 30 seconds behind, according to the Zoom documentation that I read. All right, so let's get started. I've got some notes to keep me vaguely on the right track here. Okay, so let's start with what this is about. So fastai version 2 is a rewrite of fastai from scratch. I'm somebody who has done a lot of rewriting projects from scratch, and I've always found it a really terrific experience. I know some people don't like it, but for me, it's been something that I've never ever regretted doing. And fastai in particular is in, really needs it. Basically, what happened was I've never created a version of fastai which wasn't under tight deadline pressure. So the kind of releases of fastai so far have always been compromises between the time I had available and what I was able to do. And yeah, since a lot of people are liking it and I'm liking it, we thought it'd be a good idea to try and create, a version, a kind of definitive version, the version that's the best that we can make it right now. And then, of course, the other thing that's happened in the last year or so, a bit more than a year, is that Sylvain joined, and so that's given us a lot more capacity to do high quality work. And then hopefully most of you have seen fastai version, the course, part 2, version 3, deep learning from the foundations. We did a kind of a, let's rewrite much of fastai as a course. And that turned out to be a good course that a lot of people liked, but it also showed, we actually ended up writing a lot of things better than the first time. There's plenty of very reasonable criticisms people have of fastai version 1. Most particularly is what I would call the mid-level APIs are not great. So the high-level APIs, if you're using stuff in the way that we kind of show them in the course, it tends to work pretty well. If you use the lowest level functions, they tend to be pretty performant and they work pretty well. But if you want to create your own data blocks, data type, or something like that, it's not particularly well documented as to how to do that, and the code to do it is pretty hairy, and it's not really as nice a layered an API as I would like. So there's kind of like plenty of bits of the fastai v1 code which were not designed as carefully as they could be, and particularly these kind of middle layers. So the goal with version 2 is to make it extremely hackable at every level, and like have lots of tutorials and examples to show that hackability at every level, rather than just showing the kind of top level and lowest level functions. Also in part 2 of the course, there were just some really big improvements, like the way we did callbacks. We're just much happier with the way the callbacks were done in the most recent part 2 of the course than they were in version 1. So yeah, that was some of the reasons. Another reason for the rewrite is I have been really happy with our kind of experiments with literate programming, by which I mean we've been kind of using notebooks more and more. I'm just trying to see here, what's the, I'm not seeing any more chat messages. Are there any chat messages coming through? I'm not sure that's working. Oh, here they come. Great. Thanks. Sorry, everybody's just being quiet. Where was I? Yeah, so kind of using notebooks has been going super well, and we wanted to see if we could use them more. And so Sylvain and I decided to experiment with using notebooks for everything. And doing kind of true literate programming, which is an idea that Knuth came up with many, many decades ago, but I don't feel like anybody's quite gotten right. Yeah, so we thought we'd experiment with that. Another thing was, as I got to know Python better, I realized that there was this really powerful core in Python that can be used to kind of build things any way you like. But the way that Python had chosen to use those things to build things wasn't quite the way I would like them to be. And there were kind of opportunities to make Python work more the way I wanted it to work. And so I kind of wanted to take advantage of that. So fastai v2 is a rewrite from scratch. There's a lot of things that look very similar. The basic high-level APIs look much more similar than different, but everything underneath is quite different. Yeah, like using decorators and meta classes and yeah, stuff like that, as you'll see. So a few things to note. The first is for intermediate Python programmers, you will probably find this the most difficult because we're going to be using Python in a way that's going to look very unfamiliar a lot of the time. And so you thought that Python does certain things in certain ways, and you'll suddenly discover that's just one way to do things. For new programmers, it'll be no problem. So people who are new to Python, you'll just learn a way to do it, and you'll be like, oh, okay. And if you're experienced programmers, like really experienced, you'll have seen lots of different languages and seen lots of different ways to do things, and you will recognize influences from other languages in the way we're using Python. But if all you've used is Python and you know, you've been using it just for a couple of years or something, then this is going to be an interesting experience because you're suddenly going to discover a bunch of new things, which hopefully you'll enjoy. So, you know, don't stress when things look a bit unfamiliar because hopefully you'll find that you'll learn some new stuff in the process. Remember, fastai is a research organization. And so I'm always looking for like, how could I do things better? And so I'm never feel like I have to do things the way everybody else has always done things. And I kind of take my time to figure out how to do things the best way I possibly can. And so you'll see that we're particularly doing that with changing a lot of the ways that Python is normally written. Okay, so that's the introduction. So yeah, so we're going to share basically all the tools and processes and try to document everything so that nothing's mysterious, and certainly everything is open source as usual. The code walkthrough, I'm going to kind of start in the middle and work down. And then at the end, we might work back up to the top again. But we'll see. It depends a bit on your questions and stuff as well. Okay, so step one is to find the code. And currently, it's in the fastai/fastai dev repo. And so you can git clone this. And once you git clone it, you will find that there is a dev folder. And in the dev folder, there is a bunch of notebooks. So step one would be to git clone that. And then you'll find, thanks to kind forum participants, that in the root of the fastai dev, there is an environment.yml, which you can use to create a conda environment. So I expect if I go conda environment.yml, there you go. You can find out how to use those. Creating environment from an environment.yml file. There you go. by default, it'll create an environment called fastai dev. You don't have to create an environment. The alternative is you could just follow the README with conda install and pip install. That will work fine too. Don't run PyTorch from master, run the version that you see here. So it has to be at least 1.2. And it should work fine with Python 3.6 or 3.7. Silva and I are using 3.7 most of the time, so that might be safest, but I have tried to recently make sure it's working correctly with 3.6 as well. After you clone, so here we are. So after you clone, there's one more thing I want you to do, which is you'll see there's a tools directory. And what I want you to do is run tools/run after git clone. So just run that command, and you just run that once after you clone. Basically what that does is it sets things up so that when you, if you like send in a pull request or something, it will clean up the notebook to remove the kind of extraneous stuff which tends to cause conflicts. And when you, so if you forget to do that and then you send us a PR, then we might complain and say, oh, you forgot to run that. So just go back and run it. So you just have to run it once. It installs something called a git hook, as you can see, post-merge hook, which every time you push or pull, it will run a little Python script that removes that extraneous stuff. Okay, so there's a question about how usable is the library at this stage. I mean, I don't know. It's okay. Like the highest level API we're still fiddling around with, but the stuff I'm going to be showing you I think works pretty well and is pretty stable. So yeah, but it's early, so you might find problems with it, and if you do, we definitely want to hear about it. We are. Let me just fix that. So git checkout 01. Oh, cd dev. Git checkout 01. Git pull. Okay. So you will notice that it's being very actively developed. So if you look at the commits, there's quite a few every day, and they're making big changes. So yeah, I think it's fine for experimenting with, and if you're keen to kind of get involved, then you should definitely try to do as much as you can with it, but don't expect it to be super stable. The other thing I'll say though is once this is done, we're writing a book about it, and this is designed to be kind of the definitive version of fastai. So once this is released, it'll be very different to fastai version 1, where the first release was something that we kind of wrote pretty quickly under a tight deadline, and then we just changed things a lot all the time. Whereas this one, we're going to try super hard to have a very stable branch and minimize API changes, at least within the same major version, and stuff like that, amongst other things, because there'll be a book that it has to stay consistent with. So it won't freeze the API like Keras has. I think that was a big problem for Keras because deep learning changes a lot, and we don't, in the end, we want a library that suits modern best practices. But if there's going to be if things change so much that we need to do a major API change, we would do a version 3, and we would try to backport bug fixes to version 2. the Swift development is quite separate to this. So there was a lot of influence from both the Python and Swift lessons from the last part of the course in terms of what we're writing. But the Swift stuff is kind of, it's largely waiting for things to change in Swift for TensorFlow around kind of MLIR and the new runtime and the new metaprogramming stuff. And it's, yeah, so it's going to be a while, I think, until Swift for TensorFlow is ready for a really good version of Swift AI. So the two pieces are quite separate. Okay, so I should try to make sure that I'm explaining the questions I'm responding to. That makes sense. Okay. Right, so where are we? Yeah, so one thing to be aware of is that you might be tempted to start at notebook 01, say, in terms of understanding the library. That would be a very enthusiastic approach because notebook 01 is actually the most complicated. And the reason it's the most complicated is because this is the stuff that kind of sets up Python the way we want it to. So it like starts with meta classes and then decorators and type checking and monkey patching and context managers. So that's going to be tough. And if you're keen to learn a lot of advanced Python tricks, it's a good way to do it because kind of all of the advanced Python tricks are in the first couple of notebooks pretty much. But that's not where we're going to start today. We're going to start somewhere much more convenient, which is at 08. And 08 is actually a tutorial notebook. It doesn't actually define any functionality, but instead it shows you how to use some functionality from the first 7 notebooks. So here is notebook 8. And so let's have a look at how these notebooks kind of work first. You'll see that the notebooks start with a number of imports. And the imports are coming from local.blah. And actually, some of these can be simplified. Instead of, see how I've got quite a few things coming from local.data.something? I could actually delete all of those and just have local.data.all. And that'll bring in everything from those submodules. Why local? Well, the reason is that, as you can see, we have a local directory here. And what happens is in the notebooks, so let's pick a notebook. Let's do, say, Vision Core. And let's simplify this one as well to do local.data.all. So you'll see, for example, in 7 Vision Core, there's a couple of interesting things. The first is default export vision.core. What that means is that this notebook is going to create a Python module called vision/core.py. Let's check. Vim vision/, oh, it'll be local though, local/vision/core.py. So here it is, right? So here's the library, the package, the module that is auto, as it says at the top, auto-generated from this notebook. And so this cell starts with #export, and that's a special tag, which means please include everything in this cell in the exported Python module. But it makes a few changes. In particular, see this line here says from local.imports, import star. That's been changed here to from dot dot imports, import star. So the thing which creates Python modules from notebooks knows that local is special, and local refers to this local repo's version of fastai v2. And so in order to export a proper set of modules, it has to replace local with appropriate relative module paths, so dot or dot dot as appropriate. So there's a little special thing that happens. But on the whole, most of the time when you see something that says hash export, so here's patch property npx, you will just see it in exactly the same in the .py file, patch property npx, okay? All right, so what happens is we have these notebooks and they have these hash export cells in them. And what we do is then at the bottom of every notebook, you'll see there's a cell that says notebook to script. And when you run this cell, as you can see, it converts all the notebooks. It takes about a second. And that's the actual thing that when you run that, it creates these Python files. So the Python files, so we could go C tags, and we could go vim. And so the Python files are just, it's just a normal module. So for example, here's a function called image to byte. So I could go :tag image to tab. And so you can, and there it is, there's image to byte, right? So like we can jump around in the usual way. So here's something called tensor image. So I could jump to that. So you can use your editor in the usual way and treat it just like a normal Python module. But what we would request you do most of the time is instead to read, edit, and use the notebooks. And the reason why is that, as you can see, the notebooks have a lot more. They have examples, they have pictures, they have prose, they have notes, they have explanations, they have context. And so, you know, this is where you should generally be looking at the code if you want to see what's really going on. So the only other thing at the top here is something which says default class level. That's not particularly important, but basically what happens is we actually create documentation automatically from these notebooks. So for example, we were just looking at, well, let's have a look at one, say core.layers. So you can see that the notebooks are turned into hyperlinked documentation. Data pipeline. And you can see that all the different classes and methods and stuff automatically get documentation added from their doc strings and also from any code and markdown around them. And these, the different classes and functions all come in at different heading levels in the HTML. So this is basically, if default class level just says, normally the classes are documented as HTML heading level 2. This says, please document them as HTML heading level 3. That's all that's for. It's not at all important. Something else that you see as you look at the notebooks is lots of things that say test. So like there's a couple of ways we could have done this, right? If we wanted to say like, how do these things work? So we've opened up an image and we can have a look at the image. Gosh, it's a tiny, tiny, tiny image. Oh, because that's been resized to 30 by 20. Fair enough. And so we could then say like, oh, we've just defined something called npx. So I could go im.n_px. And it's 600. So like one way we could document this in the notebook is by like writing something that prints out answers. But what instead we do is we add a test, which says test for equality im dot n underscore px comma 30 times 20. So in other words, im dot npx will be equal to 30 times 20. So we use the tests and they're going to appear in the documentation, right? And so that's when you read the documentation, it's telling you what the result of this will be. But it's doing two things. As well as telling you in the documentation what the result of this will be, so you understand how it works, it's also creating a test to see whether it's working correctly. So then if you look in the repo, you'll see in the README, there is a way to run all of the notebooks as tests in parallel. So you can check. And basically, they should all basically pass pretty much all the time, except, you know, at the moment, we're still under pretty heavy development, so not everything passes all the time. But if you notice something failing, feel free to tell us because, yeah, we want to have everything passing. Okay, so we'll get back to actually what things like @patch property do later, but this is more of a kind of demonstration of how we end up with all of this from local dot stuff, right? So all of these have come from notebooks. So this notebooks, the test ones are coming from, so yeah, so for example, where does test underscore EQ come from? It comes from a notebook called 00test. And so here, let's find it. Here is test equals. Okay. So, and we'll eventually get through it and see how all this code works. So what's going to happen eventually is that when we create conda and pip packages out of this, rather than creating a directory called local, it's just going to create a directory called fastai. And then internally, it's all going to be exactly the same. So this will be super easy to generate normal pip and conda packages from. So let's take a look. So here is 08 pets tutorial. And so let's go through and see what we've got here. So the first thing we import is local.imports. Local.imports is special. It's the only Python module which is not created by a notebook. It's just created by hand. So here it is. And as you can see, it's basically just a bunch of imports. I am thinking, we haven't quite decided, but I am thinking we might split some of this out into a kind of a core library that doesn't require PyTorch and another bit that does, and maybe split out some of the things like the testing and the notebook stuff into separate repos. But at the moment, everything's in one place. Other than those imports, there are 1, 2, 3, 4, 5, 6 functions defined in imports. And yeah, that's about it, as you can see. So that's what imports is. Then test is the test notebook we just saw. Core we'll be talking a lot about, but it's basically the kind of core functionality that I wish was in Python or PyTorch, but isn't. The data modules are all the stuff to do with transformation pipelines and stuff like that. Then we've got separate vision, text, tabular, etc. applications. And so that's that. So this will look pretty familiar from FastAI version 1, which is that I can call untitled data, for instance. So we can start to look at the pets data set. So you can always, of course, just go untitled data, question, to see the source code. And generally speaking, we're trying to make it so that all of the functions and classes pretty much fit into a screen of code, as you can see happens with this one. Okay, so this will, just like in version 1, will download from urls.pets and untar it if not already done so, and will return a path object for where it's been put. And the default paths are still the same as version 1, so .fastai/data. All right, so again, something which is basically the same as fastai is get image files, which is a super fast way to grab a bunch of files. Get image files just calls get files, passing in a list of image extensions. So it's just going to get a subset of the files by extension, and then get files is pretty much the same as it was in version 1. It's an extremely fast way to grab optionally recursively all of the files in a directory. So for pets, we can grab it like so, all of the files. And so what we're going to try and do is we're going to try and load pets using a minimum of fastai functionality. We're going to try to use like only the lowest level functionality. So we're going to do a lot of stuff very much by hand. So as you can see here, one thing we're doing is using the random splitter. Which is a class. Well, it looks like, actually it's not a class, it's something that returns a function. But basically it's something which will give us a function that will return a random bunch of integers of some size. So for example, in this case, we've got split idx. So that has 2 things in it. And they are the indexes of the training set and the validation set. So why are we using capital letters, which we normally only use for classes? We basically decided that anything that when you call it, it returns something which you still then have to call things on, we use capital letters. So random splitter is a function that returns a function. So it kind of looks a lot like a class. So that's why it's capitalized. Okay, so this is going to be a list of the indexes in the training set and the test set. And so then that will be used combined with our items to decide which paths are in which spot. Okay, so let's see how we can use this. The goal will be to do this. It will be to create a picture of a dog and tell us what kind of dog it is. So we've got our list of paths. We've got them split between training set and test set. So we need a function that can open an image and resize it to some fixed size, and then turn that into a tensor with the channel axis first between 0 and 1. So let's write that function. And then the next thing we need is a class with a method called show, which is capable of displaying an image and a title. So one of the things you'll see that we have is a function called show titled image, which simply calls show image, passing in the first thing it's given as the image and the second thing is given as the title. And so what we're going to do is we're going to, data sets basically have return tuples. So in this case, the X will be the tensor containing the image and the Y will be the name of the class. And so why do we have this class with a special thing called show? So here is the first bit of kind of new API to tell you about, which is this. Any class that has a show method is something which can be kind of used by the whole fastai transformation system, so that you can basically say dot show, and that's how dot show is going to work. It's going to try and find a type which has a show method. So the first thing, well, one of the steps we need to do, therefore, to get to this point is to create a class with a show method. And we already have lots in fastai, but we're going to we're trying to show you how to do this using no outside functionality in fastai, basically, except for transform. So that's why we're doing everything by hand. So you'll see that this says titled image. And then you'll see in the next bit, we create a pitt transform, which has a type annotation on the return. This is a big difference between fastai version 2 and fastai version 1, and between fastai version 2 and every other Python library I've seen, which is that we use type annotations in version 2 a lot, not for type checking, but actually to make certain behaviors happen. So I'm going to be telling you a little bit about this class called transform today, but a transform is basically a function. It's actually a reversible function. It's something that you can encode to turn, in this case, a path into a tuple of an image and a label, or it can decode, so it can go the opposite direction, going from a tuple of an image and a label into a titled image object. Now you'll see here, it's actually returning a tuple. It's not returning a titled image object. And the reason for that is that the return type annotations in fastai transforms actually cast. They actually cast the data into this type. So this is not just descriptive, it's not just documentation, it's actually changing the behavior. So let me show you. So let's run these cells. So if I go, I'm going to go through all these lines in a moment, but if I create a pets transform object and I grab, I pass an item to it, and then I go decode, you can see I can go decode.show. If I go type decode, it's of type titled image. So this is something that we use all the time in fastai version 2. And to people who are experienced Python programmers, this is going to be extremely surprising because Python doesn't normally work this way. But we found it unbelievably useful. It's made so much of our code simpler, shorter, less buggy. So we are using types a lot in version 2, but in a totally new way. And so we'll be showing you how we do that over time. But for now, I'm just going to tell you what you have to do. Right? So if you want to create a function that can convert, for example, I've got here items 0. So item 0 is a path, and we've got a function. So we could create a function. Let's just do the function version. We could just create a function like this, right? Def pet function. And we're going to take an item. May as well call O to be simpler, right? And so then we could go x comma y equals pet function O. Sorry, item 0. Oh, whoops, and that would be O to I, and that would be, let's see, labeler, labeler. Okay, Oh, there we go. There's X, or we could go show image X, right? And we can see Y. But you know, the issue with this is that X has no semantics, right? X is like, and nor does Y. Like these things have no semantics. Like, what's the type of Y? It's an int. You know, how do we display that? How do we know what it is? How do we know what it represents? How do we do things to it? Same with the image, right? Like, it's a tensor. We know it's not just a tensor. We know it's a tensor that represents a 3-channel image. We should be able to rotate it. We should be able to brighten it. We should be able to flip it. But in PyTorch, there are no semantics associated with, you know, kind of domain-specific semantics associated with a tensor. So a lot of what we do in fastai v2 is to add these semantics to these tensors. So in this case, what I really want to do is change this to a titled image. And so I now can say, you know, whatever t equals titled image, that's a tuple. And then I can go t.show, right? And so now I'm getting closer, right? So we use O quite a lot. It generally just means some object. Sometimes we use X. I'm trying to get in the habit of using O. That's a bit annoying here. I've used O in one place, next in another. Plenty of room for improvement in our notation still. So you can kind of see how if we can add types to things, we can give things functionality so that then the users of our library can just rely on things like, oh, I can always say .show. Or if something's representing an image, I could do .rotate or .flip or whatever. So that's kind of one piece of this. The second piece is, you know, it's not okay to see 21. We want to be able to see Great Pyrenees. So that's why everything that changes your data in a way that kind of removes the ability to know what that data is, that it should always be able to also go back to where we came from, to be able to display it again. So in this case, this is basically what our transform subclasses are. Transform classes are things which know how to take some input data and convert it into something which you can get closer to modeling with. But anytime that's kind of losing information so that we can no longer display it and understand it, you also show how to reverse it. And so for something like this, where we actually need to know what are the, what's our vocab, basically, what are the possible types of pet breed we have, that's some state we need. So that's why these things have to be classes, right? So in the init here, when we create a pet transform, we're passing in a vocab. So here vocab is just a list of all of the possible pet types that we saw. And then we have O to I, so that's object to integer. So that's just a reverse mapping. As you can see, that's the exact opposite. And what we're trying to do in fastai version 2 is where things are really commonly used stuff, we try to make them directly available. So the uniqueify function now has a bidirectional parameter that we'll look through in all of the values, which in this case is all of the labels. Let's have a look at vals. That's annoying. Let's do it this way. Just going to do it like this so we can see it better. Okay, so you know this is just all of the pets that are in our data set for every image. So uniquify is going to go through and find all of the possible unique values, and it's going to return the unique list in sorted order, as well as the reverse mapping. That's why bidir is here. So that's everything that we then need, nearly, to create our pet transform object. The other thing we need is we need to tell it, how do you convert a path like this into what kind of pet this is. And as we saw in lesson 1, for pets, you can use that regular expression. So a lot of the labelers and stuff look the same. Regex labeler. So these things are super simple, right? And again, this is actually not a class. It's a function that returns a function, but it kind of feels like a class that's still got these capital letters. So we can now put all this together. So step 1 is to create a function that will label paths. So turn a path into a type of pet string. Step 2 is to label everything in the training set. So that's why we use items split IDX 0, because we just want stuff in the training set. Step 3 is to create our vocab and the reverse mapping. And then we can pass those 3 things to our pet transform, which simply stores them, as you see. And so now that we have those things, we can pass a path to pets. And the way that transform works is that if you just treat the transform object as if it were a function, it will call the encodes function for you. As you'll see, it does a whole lot more, but this is the really simple version. So we're going to start there. So when I go pets item 0, it will call encodes. So it'll go resized image, comma, object to int, and the labeled version. And so that's why we get this. Okay. So that's something we could start to create a mini batch from for modeling. And then if we go decode will call decodes, which will create the tuple, wrap it in a titled image, and a titled image has a show method. And so we can show it. Okay. So that is step 1. So understanding the transform pipeline is one of the kind of more interesting things if you want to learn how to really extend FastAI version 2 and kind of into other domains and stuff like that. And so here's a good place to start, because as you can see, we're using almost no functionality other than this one class called transform, and the transform class, we're only using the very simplest functionality from it. Everything else is in this notebook. So this is stuff which hopefully you can pretty much understand yourself. I'll give you a little hint of something though, which is, what is items? Items is the result of get image files. It's a list of paths. But as you can see, it doesn't look like most lists. It starts out by saying how many items are in the list. And then it only shows the first 10 things and then ... It's got much nicer behavior than normal lists. Also, we are indexing into it with a list, which you can't normally do with Python lists. So one of the things we actually put a lot of effort into FastAI version 2 is we didn't really like the Python list, so we created our own. So if you look at the type of items, you'll see it's actually of type L. This is the only thing that has a 1-letter name in all of FastAI version 2 in terms of stuff that's in the API. But since it's actually something that we want to be a total replacement for list, and we always use this instead of a list, we think it deserves that very special 1-letter name. So L is a class we're going to be learning a lot about. It does a lot of things. But basically, it looks like this. It looks just like, so I could write list here instead of L, right? And, oh, and lists are much more awkward, but I'll have to remember. And I can do that, right? Or I could replace, anywhere you can write list, you can also write L. And it'll do exactly the same thing. And just like a normal list, you can index into it. But unlike normal lists, you can index into it with lists. Unlike normal lists, you don't have to remember to put things in square brackets. Unlike normal lists, you can index into it with masks. There's all kinds of things you can do. And even like simple little things, like with a normal list, let's do both. Let's go B equals list. So you can always do this, A plus 9, B plus 9, oh, B plus 9. So for example, with a normal list, you have to remember to listify anything that you append to it. With an L, you don't. Also with a normal list, you can't stick stuff on the front, or else with these lists you can. So there's a lot of these nice little things. Anyway, there's 1,000 more things, but generally speaking, you'll find anytime you see something that looks like this, hash and then the number of things and then the list, that's an L. You can also do things like multiply. And as you can see here, now it's going to go dot, dot, dot because there's more than 10 things in it. It does a lot more than list comprehensions, but you certainly can use list comprehensions. O times 2 for O in A. But perhaps more interestingly, you can do things like L dot mapped, operator dot neg. What did I do wrong here? Oh, not L dot mapped, A dot mapped. So there's the negative of everything. Anyway, so that's what items is. That's why we're able to index into it with a list. Now this is not a great transform because we kind of created all this stuff externally. So try 2 in 08 is we're going to do all that stuff internally. So this time we're going to create something where these cells are exactly the same as we had before. But this time we're just going to pass in the list of path names and the index of the training set. And so now we'll create the labeler inside there. We'll create the vocab and O2I inside there. We will look up the path there. And so again, I'm not showing you any new functionality here. I'm showing you more just a nicer design of a transform. There's just a little bit, tiny little bit more going on. But so with this, we can now create a transform. And just like before, we can decode it. And away we go. Okay, so that's the very simplest version of transform. In practice, as you know, in deep learning, you almost never have just one step to go from your source path or whatever to your modeling data. Normally there's a number of steps. And so to do a number of steps, we've created a simple class called pipeline, which you can see here. What pipeline does is it lets you apply a number of transforms in order and it composes them all together for you. And so I'm really excited about this example. I think it's super nice. I'm going to show you how to create a Siamese data set. So for those of you that haven't done Siamese deep learning before, Siamese deep learning is where you, well, here's an example. Your data will generally have two things. It will have, if it's a vision model, it will have two images and a Boolean. The two images, in this case, are either the same breed of pet or a different breed of pet. And the Boolean is true or false, depending on whether they're the same or different. So here's an example: true, false, false. The reason that we do Siamese models is, for example, for face recognition. You don't want to create a model of every single person's face and have like some huge dependent variable of the entire population of the world. So all you instead do is you create a model that says, is this face of the same person as this face? Here I've created a transform, which again, as input, it's going to take a list of paths. And it's going to take a list of labels, which is what breed is each one. I sort the labels and I create a map from each breed to where they are. Oh, yes. So basically, I don't need to go through all the details of the code here because this is just Python. But the interesting bit is in the encodes here. I basically randomly decide 50% whether or not the second image is going to be of the same breed as the first image or a different breed to the first image. And then I return a triplet, a tuple, with the two images. So this is the ith image, the one you asked for. This is some random other image, which is either the same breed or a different breed, 50% chance, and a Boolean saying, are they the same or not? And then secondly, I need to use that resized image function that's going to take our path and turn it into an image and convert it to all the same size. And then I need to do those two things in order. First this transform, then this transform. And that's why I then use a pipeline. So I create my Siamese pair transform, and then I create a pipeline which contains two things. First the Siamese pair transform, and then this open and resize transform. So now I can pass in, say, 0 into my pipeline, and I'm going to get back 3, 1, 2, 3 things, which is my first image, my second image, and my Boolean. And so here they are, my first image, my second image, and my Boolean. And of course, to be able to show that, we need something with a show method. Okay, so here is a Siamese image with a show method. So that means we can now create a pipeline. And let's now put 3 things on it. The Siamese pair transform, the open and resize, and then the Siamese image.create, which is simply going to cast it. And so now we can display. So that's pretty cool. And I've got a few cool things to show you, one of which is going to be slightly mind squishing. First of all, I'll show you the quick, easy one, which is another nice part of L, which is item got. So for those of you that don't know, in Python, it's got something called operator.itemGetter, which basically works like this. You can create a function, and then if I create something which has a number of different things in it, like this, then I can go, let's see, yes, I can go list map F, comma, T, and it gets me the 0th thing from each list, right? So that's what item getter does. So one of the nice things in L is item got, which basically does those 2 steps at once. Where it gets really cool though is that it actually also has something called attribute, which will grab a particular named attribute from everything in a list, and it's got some things which make it a lot nicer than Python's, like it handles defaults for things that are missing and stuff like that. Anyway, you'll keep seeing these little handy things in L, which make life much easier. Now for the one that's kind of amazing, which is, let's have a think about what's happened here. This has returned a tuple. A tuple has a pillow image, another pillow image, and a Boolean. And that is the first thing in our pipeline. The second thing in our pipeline says return resized image. So how can we possibly be applying this function to this tuple? You can't, right? This is meant to be a path, not a tuple containing two paths and a Boolean. So the trick is another nifty thing in transform, which you may have guessed is this type annotation. This is not a return annotation this time. This time this is a parameter annotation. And what this does is it tells the transform system that this particular encodes only works on paths. And so what this does, actually we can make this a little simpler. Tuple transform. Let's get this the right way around. Yeah, there it is. So there's a subclass of transform called tuple transform, which will, if it gets a tuple as X, then it will run encodes on every element of the tuple separately, and it will only apply it to those of this type. For those that aren't of this type, it will just ignore them and pass them through. So this is like, it'll turn out to be super, super handy for things like data augmentation, where basically you can define, so you can actually literally, as you'll see, have multiple different encodes methods for multiple different types, and it'll automatically pick the right one. And so we'll use this a lot for things like defining a single data augmentation, which behaves differently for images versus masks versus point clouds versus etc. So again, this is something that's used all the time in FastAI version 2. It's not at all weird in lots of languages. So for example, in something like Julia, this is how all of Julia's type system works. But it's not something that is very often seen in Python. It's not unheard of, but it's not common. I'm not sure I've seen anything that quite combines OO and dispatch in this way before in Python. And I've seen some things that are similar. So this has been quite nice for us because we were able to create this single pipeline which will only open and resize those things which can be opened and resized. And specifically that is paths. Okay, so a question was, if I have a list of numpy arrays and torch tensors mixed, can I use this to convert only the numpy arrays to tensors? And the answer is yes, absolutely you could, except it can't be a list, it would have to be a tuple. So this just specifically works on tuples. And the reason for that is that PyTorch's data loaders will work on tuples. So that's how this works too. So you can see here a Siamese image then, we've got our show, and yeah, that's that. So that one is a pretty interesting example. Lots to think about there, as you can see. And by the way, tuple, if you're wondering, like, is tuple transform, like, what's the difference between tuple transform and transform? That's the entirety of tuple transform. A tuple transform is simply a transform which has a single parameter set. So basically all transforms know either that they act on over tuples or they act over a whole item at a time. So that's not really a separate class, it's just a convenience. Okay, so we've got transforms and we've got pipelines. So kind of building up this intermediate data processing pipeline. The next step is that you would generally want to apply a pipeline to a list of items. So for example, in this case, a list of paths to pets. So we have something called a transformed data set, TurfMDS. And as you can see, it applies transforms or pipelines to items of a collection. So basically, what this is going to look like is we're going to create, we're going to be creating a TurfMDS. We're going to be passing in our items. Again, that's still our list of paths, just to remind you, items. And a list of transforms. And this time it's going to give us something which we can subscript into. So it'll behave a lot like a list, except it's a list where these transforms will be lazily applied to the item. So items 0 is this particular pet, whereas TDS 0 will be that particular pet with this list of transforms applied. However, it's not just a list of transforms, it's a list of transforms. There's list number 1, there's list number 2, and that's because in practice in deep learning, you nearly always have at least a independent variable and a dependent variable. So an X and a Y. List number 1 defines the transforms in the pipeline to create your independent variable. List number 2 is the transforms in your pipeline to create the dependent variable. So, and you can have more than that. You can have 3, 4, 1, as many as you like, but the vast majority of the time, it will be 2. So let's look at an example, right? So items 0 is this path. So in pipeline number 1, all these are going to be composed together. So it's first of all, it's going to create a pillow image. And then it's going to resize it to 128 by 128. As you can see, we've got a little transform above here, which knows how to resize. And then it's going to convert it into a tensor. And then it's going to convert the byte tensor to a float tensor. And so that is a pretty standard, simple pipeline for creating a ready-to-model tensor, except we haven't batched it yet, from a path. Pipeline number 2 is going to start with our labeler, which was that regex labeler we saw earlier. And then it will pass it through categorize, which is something which knows how to create a vocab. And so the two things together is going to give us a tuple containing an image, and let's do it this way. Oops. Let's see, what have I done here? Okay, so this is good to have some debugging to do. So in our labeler, it looks like we already have a label. So why is that? So we're passing in items and going setup. That's our setup path. That's our category. And then unique. Okay, I'm not immediately sure what that is. It's something that I was just changing earlier today. So I've just introduced a bug that I will fix this afternoon. The question being asked is about what we mean by lazily applied here. So the key issue is that there's two ways we could do this. We could take this list of items and we could apply this pipeline and create all the images we want, and this pipeline and create all the labels we want. And we could do that once and kind of store that all in memory and then just grab them when we need them. There's two problems with doing that though. The first is that for something like ImageNet, the images are too big to store them all in memory. So we wouldn't want to do that, and it would take a really long time to open them all. And the second is that often transforms will have random stuff in them, such as my Siamese transform, or if you have data augmentation. So in practice, what we want is for these pipelines to be applied only at the moment when I actually ask for a particular item. And so that's what lazily applied means. It means that the function is only called, the transforms are only called when we request the particular item. So I've had a couple of questions now about CPU and GPU, so I may as well mention them now. So when we do stuff like ImageNet, it tends to use up a lot of our CPU. Often it's actually our CPU doing the transformations, which is the bottleneck. And so, and this is why, is because pretty much all libraries work this way. They lazily apply the transformations, and even just like opening a JPEG takes a long time. So one of the things we've actually done, as you'll see, is nearly all of the transformations or the more complex transformations in fastai v2 are actually run on the GPU, not on the CPU. And part of the reason we're able to do that is because of this type system that I was telling you about. So you will see that shortly. Something else to notice here in image resizer is that encodes is defined twice, which normally would be meaningless in Python. The last one would override the first one. But because this is a transform subclass, we actually have this magic dispatch stuff happening. So if this transform receives a pillow image, then it's going to resize it using self.resample, which is a bilinear resampling. If it receives a pillow mask, it will resample it with a nearest neighbors resampling. And this is important because for masks, you can't do bilinear resampling because you end up with floats instead of ints. And so this is an example of where like you can use this type dispatch system to automatically dispatch your function to the right behavior depending on what kind of data you're using. And so you'll see that not only do we have now types for tensor image, black and white, tensor mask, but we also have types for pillow image and pillow mask and so forth. So we've got a lot more semantic subtypes of commonly used libraries that's used to make all this stuff super, super, super easy. So now if our bug was fixed, then we can grab the 0th item of our transform data set. That will grab item 0. It will pass it through the 2 pipelines and it will return a tuple, which we can then later on decode to get back a decoded tuple, which we can show. So this is basically, yeah, the same behavior. But as you can see, we've got both a lot more functionality going on, and we're also starting to use some built-in stuff that's built into fastai version 2, like categorize and PIO image.create and to tensor and stuff like that. Generally speaking, most of the fastai version 2 types will have a .create class method, which is used to create one of those things. So PIL image.create, for example, can be passed to path, like so. And so that's used in a number of places in the library. When it's expecting to be able to create something, it's going to look for a .create method most of the time. Okay, well, I think that is enough for now because data source is, well, yeah, I think so that's enough for now. That's quite a lot to sink in. So I'll let you have a think about that and do some reading and ask any questions you like. My only request is that, well, I've got a couple of requests. One is that Sylvain and I are pretty busy trying to write the library. So if somebody asks a question on the forum that you can have a reasonable guess at the answer to, yeah, please try. That would be super helpful. The second is, yeah, that on the forums, there are some, you see like fastai v2 core, tabular text transforms. So it'd be super helpful to like go in and start to fill in this wiki topic, which I think is a wiki topic. Yes, it is, with some kind of documentation and notes from today and stuff like that. That would be super helpful. And then, yeah, tomorrow we'll start to look at data. Well, we will look at data source. That won't take too long. And we'll see the segmentation example. And then from there, yeah, I'm not sure we'll go from there. We'll see. Happy to take suggestions after some of you have looked at the code. Thanks very much for joining in. And yeah, a reminder next time, if anybody wants to have more of a conversation about something, feel free to say so, and I can add you as a participant and you can talk as well as text. Okay, thanks everybody. Bye.